a machine learning engineer at Hugging Face, and I work on large language models for code. And today I will tell you how these models are trained and how you can leverage them for your own use cases. So a few words about me. I work at Hugging Face, and I did my studies in Paris on engineering and deep learning, and I mainly now work on LLMs for code and synthetic data. So let's see a little bit how all of this started. Large language models for code have been there for a while, but this topic became very trendy in the AI world when GitHub Copilot was introduced in late 2021. So this is a VS Code extension by Microsoft that auto-completes your code, and it uses a model by OpenAI called Codex. And this was a very huge breakthrough in the field because this model was so much better than all the other code completion models before it, which were so much smaller and much less performant. And this is important because it kind of improves the productivity of the engineers who use it. Not all of them, but some of them. For example, it can help you write unit tests or documentation, or even do more complex tasks with the recent LLMs that we have now. For example, in this blog post by Google AI, I think it was in 2022, they found a 6% reduction in code iterations. And if you scale that to hundreds of thousands of engineers, this is a significant gain of time and money. This was very exciting, GitHub Copilot, AWS Code Whisperer, and other models, but the issue was that they were only available through an API, so you don't have the model checkpoints. You can use the model to fine-tune it on your own use case. You also don't have information on the data that was used to train these models, so there isn't a lot of data transparency around, and also the code to do the training and data processing is not available. So all of this makes these results not reproducible. But if you go to the Hugging Face hub, where you can find all the open source models, and you search for the tag code, you can see that now we have over 1,700 models that are trained on code. Some of them are LLMs that included code in their training data, but a lot of them are pure code completion models. So we've made a lot of progress in this field. You might be wondering, how did we get here? This is the product of the community's work to train code models that not only can auto-complete your code, but that can also follow instructions, and that we call them instruction-tuned. And if you go, for example, to this code leaderboard that we made, where you kind of rank code completion models and compare them on different programming languages, you can see that on some benchmarks, the scores are pretty high. For example, solving more than 80% of the problems in the benchmark for some of the instruction models for code that are out there. So there's a lot of progress in this field, and there are a lot of interesting models that you can use. But how are these models trained? If you want to train an LLM in general or an LLM for code from scratch, you should know that this requires a lot of resources. First, you need to have a lot of GPUs to be able to train the models in a reasonable amount of time. This can go from hundreds of GPUs to thousands or even more. You also need to have a lot of data, because generally these LLMs, they require terabytes of data to train them efficiently. So you should be able to scrape all of this data, to filter it, and then to train on it. You should also be able to scale the performance, because once you have the data, it's not like you're going to take the model to figure out which filtering makes sense for your data set, which hyperparameters make sense for the model. So that will require like a team who's able to dedicate effort and time to do all of these experiments. So training models from scratch are not for everyone. It requires a lot of resources. And if we look at the technical details very quickly, these models, they usually all have the same architecture, which is a transformer model. And then first you start from a model that is untrained, and then you show it a lot of data. It becomes a pre-trained base model. And then you show it some data where you have ground truth. So this is called supervised fine-tuning. And after that, you can do another step called RLHF, which is alignment, to get the model to hallucinate less, to generate less biased content and toxic content. The aim is to align it with human preferences. And this is when you get a chat model, for example, like ChatGPT. ChatGPT went through all of these steps. And for us, we want code models. So we're not going to train on just the web. We need to train the model on code. Where do we get that? We get the data set from GitHub. And then if you want to build a model that can follow instructions, then you need to build a data set for the SFT step. And it looks like this. For example, you have an instruction, write a function or solve a bug, and then you have the solutions, which are the ground truth, and then you train your instruction-tuned model. And that's how you get a chat LLM, but specific to code. So I told you that you need a lot of resources to train these models from scratch, and not everyone can do that. We're very proud to be part of these people who train these models for the community through a project called Big Code. In this project, we released the Stack dataset, which is the largest open dataset of source code. We also released 2 families of code generation models, StarCoder and StarCoder 2, in different sizes, along with an instruction-tuned model called StarChat2. Other players in this field are Meta with their CodeLlama models and DeepSeek Coder with the DeepSeek models. There are also other models, for example, from Stability AI, CodeGen from Salesforce, and other LLMs. So all of these models are open. It depends, how open depends on the license that they are released under, but you can find the checkpoints and you can adapt them to your own use cases. So I've told you some of the things that we developed in Big Code, but what is actually Big Code? It's a collaboration that is between Hugging Face and ServiceNow, and our goal was to have an open project where everyone can join and can help us train these models in an open and transparent approach. So for example, in our Slack channel, we have over 1,000 people who joined. These are researchers, engineers, but also lawyers and policymakers, because we really also care about the data governance and privacy aspects, and we wanted to invest some time into that. And the pillars of this project are 3: full data transparency. For example, if you want to use our models, you can know exactly on which data they were trained. This data is public and you can inspect it. We also open source the code for processing the data sets and also training the models to try to make our work reproducible. And the model weights are released under a commercially friendly license. And the motivation behind this project was to kind of try to encourage better practices in the field of AI and the LLMs in general. These practices are not always respected in the closed source field. For example, you might have a model whose weights are public, but the details about the training data are not disclosed. This might be because they're afraid of lawsuits, but also to not give up their competitive edge to others. Sometimes the model weights are not public, for example, which is the case for ChatGPT. And if we want to use these models, or for example, even use GitHub Copilots, the issue is that you will have to send your data to a third party because you're just querying an API. And in a lot of cases, your data might be sensitive, so you don't want it to be sent to third parties. That's when you want something that is deployed on-premise and that is secure. And needless to say, that all of this makes this work not reproducible and doesn't encourage progress in the open source field. What we're trying to achieve with this project is to have, for example, public data. The data that we trained on is available and people can inspect it. If they want to be removed and not be included in our future trainings, they can just fill a form and opt out. And the model weights are public for fine-tuning, and you can also deploy them in-premise. This is the dataset we released. How we built it is that we basically scraped all of GitHub, and then we filtered the dataset for licenses we can use, and then we did additional filtering, like removing files that look similar in a step called deduplication. We also have a tool called Am I in the Stack, where you can go, you can just type your GitHub username, and you can check if any of your repositories are in our datasets. If you don't want to be in the dataset and in the model trainings, you can just fill a form, and we'll make sure to not use your data. This is the first model that we trained. It was released last April. It's called StarCoder. It has 15 billion parameters, and it was trained on 500 A100s for 24 days. And when it was released, it was the best code generation model. Last month, we released a new data set called the Stack V2, which is much larger than the first version of the Stack, and also still the largest open data set of source code in collaboration with Software Heritage. And we also trained a new model called StarCoder 2, which is much better than StarCoder and also better than a lot of other models there. So for example, if you want a 15B model, the best model is StarCoder 2. It even outperforms other models like, I think it's not here, but it's CodeLlama 34B. And it's good on code, but also math. Another thing we added in this model compared to StarCoder 1 is repo context. So before, when we were training, we would just grab files from GitHub and randomly concatenate them and train on them. So we kind of lost the repository level structure. But for StarCoder 2, we made sure to keep files that are in the same repository next to each other during the training. So this StarCoder 2 model is aware of repository context. And if you were to use it, for example, in a VS Code extension and concatenate files from your repositories, it can give you completions that are in other files and not necessarily in the file that you're editing. We also built an instruction-tuned version of StarCoder 2 called StarChat 2 in collaboration with the Hugging Face H4 team. And this model is available on a space that's Hugging Face. I think I put the link there. And you can query it. It can also complete your code, but it can also follow instructions, not just on Python, but also on other programming languages, because StarCoder 2 was trained on more than 600 programming languages. This kind of creates a big code ecosystem where people would take the dataset that we released because it has so many programming languages and develop new models on top of it. So this can be new pre-training from scratch, for example, like stablecode or CodeGen 2.5 and other models. Or people would just start from the models we released, for example, StarCoder and StarCoder base, and they would fine-tune them for their own use cases. For example, here you can see that there's Wizard Coder, which is an instruct-tuned version of StarCoder. There's also Default SQL Coder, which is very interesting because it outperforms GPT-4 on SQL, and they just started from StarCoder and they fine-tuned it on a lot of human annotated data for SQL, and they were able to outperform GPT-4 on that. So this shows that the power of open source, when you release models and tools for the community, they can use them and build new things that even you haven't thought of. Now let's see how you can go from a model to an API or a tool like a VS Code extension. So first you have the model, and then you wrap it around an inference endpoint with an API. Then you have a chat interface. And each time you go to another level, you need to add new parameters. For example, when you go to from the model to the API, you need to add moderation and compute. When you go to the chat interface, you need to have a system prompt for the model to kind of control its behavior. You also need to have some hyperparameters to have a very nice user experience. So this is for chat models in general. If we go to code models, you can maybe just swap the last component of a chat model with a code interface. That could be a VS Code extension or JetBrains or something like that. Hugging Face released two things for that. Hugging Chat, which is like ChatGPT, but only uses open source models. It's free to use. We also have an extension called LLMs VS Code, and we deployed StarCoder there, and we also deployed other open access models like CodeLlama and DeepSeek. You can all find them there if you want to use an alternative to GitHub Copilot that uses open models. Now let's go back to this slide. I said that to train code models from scratch, you need a lot of resources. But the good news is that if you only want to customize existing models to your code base or to new data sets, you don't need as much resources. And this is possible thanks to fine-tuning. And the reason why we would like to fine-tune and not just train from scratch might be related to the resources. If you don't have enough GPUs or if you don't have enough data, because training from scratch, it requires a lot of data to get good performance. Or if the model that is already out there is good at your task, but you just want to improve the performance a little bit, you want to reduce the hallucinations, you want to include the information that is more up to date, that's when you would go to other solutions than just training from scratch. If you want to adapt an existing code LLM or LLMs in general to a new task, there are some less intensive ways and other ways that are more intensive. The easiest one would be to just do prompt engineering. You would take a chat model and just tweak the prompt to get it to solve your task. Another thing that is a little bit more complex is in-context learning, where you would add examples in the prompts to kind of teach the model new behavior. For example, there are a lot of papers who are trying to use models, for example, ChatGPT, and try to teach it new libraries that were not included during the training, and just by adding documentation to the context to see if the model is able to pick up new skills that it wasn't trained on. Another thing is tool use. I'm going to show later how to do that. And then there's fine-tuning, and then there's continued pre-training, which is like fine-tuning, but it is so much longer. For prompt engineering, as I explained, you just need to change the prompt and add instructions to kind of get the model to follow what you want. And some examples are, for example, few shots, where you add examples of the task you want. There's also chain of thought, where you try to get the model to solve a problem using step-by-step reasoning. This is, for example, very useful for math problems, where instead of just asking the model to solve it, you ask it to reason step by step and kind of split the problem to smaller, easier problems. The other thing that is also very interesting to use with code LLMs is tool use. For example, if you pick a general code LLM or just LLM in general, they might be very bad at arithmetic. And if you can plug in a calculator to do the computations for you, or just add an interpreter to interpret the code, that might help you improve the performance a lot. Other techniques that are used are, for example, RAG, retrieval. You can do that with the chat code LLMs if you wanted to retrieve some documentation and add it to the context, or if you want to add more up-to-date information to the context. And for fine-tuning, you would start from a base pre-trained model, and then you can show it some SFT data. For example, for LLMs, this can be any domain, finance, medical domain, or summarization, and then the model is able to pick up this task. The only drawback is that you need to have this SFT data that kind of has pairs of questions and answers to be able to train the model on that. So if you have it, you might be able to adapt the model to your own use case. Now let's see what are some good practices if you have a code base and you want to take an existing code LLM and adapt it to your own code base. And here I'm going to put this blog post, which is very interesting, by engineers at Hugging Face who tried to build a personal copilot. So they took some of the Hugging Face libraries that were released after Star Coder training, and they built a new code base and got the model to learn these new libraries and to kind of follow our practices for coding. And in this blog post, they go through the steps of data processing, model fine-tuning, and also provide the code to be able to reproduce their results. If you want to do that, I think the first step is you need to prepare your data set. So the steps for preparing the datasets are very similar to the steps that we use for pre-training. When we were pre-training Star Coder, we first gathered all this data from GitHub, and then we did some filtering to kind of remove files that wouldn't help the model during pre-training. And we did another filtering that is very important. It's called deduplication, where you remove files that look similar. Because for LLMs, this really hurts their performance if you show them files that are very similar early in the training. So it's very important to remove duplicates before you start the training. And for filtering, I think if you have a custom code base, maybe you already are cleaning it. But if it's not the case, you might want to have some filters to remove auto-generated files and maybe filter configs, filter SSV data, because that's not something that's going to teach the model how to code. After you've done all this filtering, then you can tokenize the dataset. Oh, sorry, I forgot another step, which is PII detection. Because in public repositories, although people shouldn't put their SSH and API keys, you might be surprised that there's still a lot of them on public repositories on GitHub. So we try to filter all of them, and we release the tools that we used. We also try to remove names on the emails. So you might also want to do that before you train your model. Otherwise, you might risk having a model that would spit out an API key or someone's name when you use it during inference. I put here some links that you can use to check how to train these kind of models. And we also have resources for data deduplication with a library called Datatrove, and we also have published all the code that we used for our own data pre-processing for Star Coder models. Let me go back to this PII reduction step because it might be interesting for you. First, we started by using regexes to detect these keys and names and emails, but the regexes were not very good at catching some types of keys. So we tried to hire human annotators to kind of annotate a data set for secrets and PII. And we released this data set. It is gated. You have to fill a form because we don't want to expose people's information. And then you can we train the named entity recognition model You just show it a file and it is able to detect where is a name, where is an email, and where is a key. And then we run all of that on our data sets. It was quite intensive because it's still an NER model, it's a neural network. And if you want to run it on terabytes of data, you need a lot of GPUs. So for us, I think it costs around 800 GPU hours on a 100 machines. But if your database is smaller, maybe it will be faster to run this pipeline. The code is also available on the Big Code Project's GitHub repository. One other thing that you might want to do is fine-tuning, but it's not just fine-tuning on 10,000 samples or 100,000 samples. It's fine-tuning on a data set that is kind of large itself. And why would you want to do that? For example, if you want to take a model that is very good at Python, but maybe not very good at Swift. And I think most models now kind of focus on Python because it's the default programming language for machine learning, and there's a lot of hype around it. But maybe you want to adapt it for a low-resource language. And if you have a data set for that, you can train the model on this data set. In the stack, we also have a lot of programming languages. So you can take one of these languages and continue training the star coder models, for example, on them. A lot of people try doing that, and it seems to help for some low-resource languages. There are even benchmarks to test the performance, not just on Python, but also on these languages. There are even data sets that were developed for these low-resource languages, like multi-PLT data sets. So we saw how to fine-tune on your custom code base and also how to do continued pre-training on data set that is a little bit larger. And now we'll see how to build a chat assistant. So if you have a code model and you want to turn it into a chat assistant that could help you with your coding related questions, you need to follow what we call instruction tuning. You need to have a data set of instructions and all the answers to these instructions. And this could be used for bug fixing or for just code completion too, or a lot of other use cases. Here there's a paper called Magic Coder, where they try to use just normal GitHub code from the stack, and they kind of used another LLM. In their case, it was GPT-4 to generate instructions and the answers to these instructions just from some code files. And this is a good approach because if you were to just select few topics, maybe you will lose in diversity, but because you start from a general code data set, you kind of get files for different topics, and you just need an LLM that can generate good instructions and solutions that actually work. I think they even try to execute the solutions to see if they are correct and they don't generate errors. And they kind of have a refinement pipeline to only keep the instructions and solutions that are actually relevant, and that will help them during the training. There's also the code interpreter paper, where they also try to do some code interpretation to increase the quality and remove the files and the instructions that fail. And if you see their evaluations, they are able to get some pretty good performances with their approach. And for example, in our StarChat2 model, how we built the instruction tuning dataset, we just took a lot of instruction datasets. Not all of them were made for code. Some of them are just general instructions. For example, write me a poem, who is the President of the United States. So these are instruction datasets that are used for LLMs. But it also helps to include them with other instruction datasets that are just dedicated to code. This way, your model doesn't lose its ability to know normal facts and also English. The model is available in this demo, as well as all the dataset that we included, and there's even an alignment handbook where you can use these techniques to do the fine-tuning. And one other good thing about fine-tuning techniques is that recently they are very cheap. You can find techniques like LoRa and PEFT, and you can fine-tune 7B models in just a few hours on one GPU. Compared to 2 years ago, it was so much expensive to train these models because you basically needed to train all of the weights, but now it's really manageable. So we saw how these models are trained, how you can fine-tune them, but you might be asking yourselves, okay, I trained a model. How do I know it's good? How the models are evaluated in the code domain is that we have some benchmarks, and we test on these benchmarks to see what is the score that we would get. For example, there's a benchmark called human eval, and it is basically some function signatures, and you ask the model to complete the function implementation. And then in the benchmark, you have unit tests for each problem, and then you execute the solution that your model generated against these unit tests to see if any of them pass, and then you kind of report an average of the problems that pass. This is a lot intensive compared to just natural language evaluation, because you need to first generate the solutions and then you need to execute them, which might take some time. Luckily, the benchmark is not very big, but that's also a drawback because you only test on a small benchmark, and it might be hard to see the differences between models that are very close just because you don't have a lot of problems in your benchmark. There are some other benchmarks that are larger, but they all require this generation then execution step. One thing to be also aware of is that what you're going to execute is code that is generated by an LLM. It might contain malicious code, so you don't want to execute it on your machine. It's better to do it on a sandbox or at least a Docker to make sure it doesn't alter your system. And this benchmark is not just for Python. I think it was translated to 18 other programming languages. So you can find it, for example, even for Lua, Swift, and Rust. And what I showed you was a leaderboard to kind of rank these models, to compare them. There are a lot of leaderboards for code now. There's also this one called Eval Plus, where they compared not just open models between each other, but they also compare to other closed models like Claude 3 and GPT-4. There's also this live code bench, and it is very interesting because a lot of people argue that maybe some of the code models are doing very well on the benchmarks because they were trained on them. Because this is what we call data leakage or data contamination. Because everyone could have taken a benchmark and put it on GitHub. So if you just scrape GitHub and you train your model, there's a very high chance that you probably trained on the test in benchmark. And so it's very normal to have a model that is good at the benchmark you're testing on. Usually we try to do decontamination. For example, for the start coder models, we checked all of our training data to make sure that none of the test benchmarks are included. But this is very hard to check if people don't say that they explicitly did that in the paper. And now there are a lot of models who say nothing about their data processing pipeline. So this leaderboard kind of tries to only use very recent repositories on GitHub and build the benchmark out of them. So there's a very low chance that the current code LLMs saw what is in this benchmark. And they also compare the open models, but also the closed models. If you train an LLM, a code LLM on your custom code base and you want to evaluate it, I think you should first start by the standard benchmarks to make sure you're not losing performance on the language you're training it on. But if you did the fine-tuning for a specific use case, for example, you want the model to follow a certain style when programming, you probably want to build a new benchmark that would test this ability. For that, you would need to have human annotators, or you can use other powerful LLMs, maybe even closed, to build this benchmark. A lot of people are doing this because it's not enough to just run on the standard benchmarks that don't necessarily test what you want to implement. Another thing is to do just vibe checks, test the model and see what it generates. And maybe the most efficient one would be to deploy the model and then have some users test it. For example, you could deploy the model in a VS Code extension and then have a number of software engineers test it. And then you can use metrics like the acceptance rate. For example, how many times is the code generated by the model accepted by the user? If this acceptance rate is high, it means that probably the generations are useful and the people want to keep them. So you can do multiple iterations and see when the acceptance rates declines or improves to kind of judge the quality of the models you just trained and deployed. But this is still kind of an intensive approach, but if you want to really test if your fine-tuning is working, you need to go through that. The last thing we're going to see is how these LLMs are served. So you can train them, fine-tune them, evaluate them, but then you need to serve them and maybe deploy them to hundreds of users, to hundreds of thousands. So depending on your use case, you might choose some options or others. We have some inference endpoints that you can use if you don't have an engineering team that will do all the MLOps side of stuff. You can just purchase an endpoint and we'll take care of the deployment. You can just query this endpoint and pay as you go. Otherwise, we have an open source library called text generation inference. This library tries to take the most popular models and deploy them in a very efficient approach. So you have your GPUs, you can use this library in the model and then be able to serve it. And what's interesting in TGI is that it has tensor parallelism implemented. So if the model is very large and it cannot fit in one GPU, it can split the model on multiple shards and be able to load it. For example, we used it with very large models like Falcon 180 billion parameters, in which was able to work efficiently. It also has token streaming. It means that when you send a query or a prompt, you have the option of like not waiting until the generation has ended and then showing. Token streaming is that like you show the tokens and the text as it is generated. And this is very useful because it improves the user experience. The user doesn't have to wait until the full generation has ended, but it can also see the generations as they come. And if the user doesn't like what is being generated, they can just stop. So this kind of reduces the perceived latency. There's also metrics for monitoring in TGI, and it is production ready. Once you launched it and you tested it, you're sure that it's not going to fail in production. It is what is being used now in our inference endpoints. It also has techniques for quantization and optimization, and it supports most of the popular code LLMs, but also general LLMs. There are other open source libraries by the community that are similar, for example, VLLM, which also offers similar implementations. So you can test both and see which one is good for your use case. If you want to explore more models and data sets related to code, you can go and search on the hub and find the ones that are relevant for your use case. You can also build demos to showcase your models and test them, and use GPUs if you don't have them. Now let's see what are the future directions of this field. I think what we really need is to have better open source models and high quality data sets. Even though we made a lot of progress, we're still, for example, behind GPT-4 in code completion and other models like Claude 3. So we still need to investigate a little bit more what is missing to kind of catch up and close the gap to closed source. We also need high quality data sets. So for example, the stack was a good step towards democratizing training code models, because it is now available and everyone can pre-train code models from scratch if they have the resources. We also need better data transparency and governance. That means telling the users exactly which data was used for the training, and also alerting about the possible biases in the data set regarding privacy and security. We also need better evaluations that not only focus on the high resource languages, but also the low resource ones. And currently we focus on functional level. So there are some benchmarks to test that the repository context works, that the model can actually retrieve information from another file and generate it. We also need better evaluations that test also class implementations, not just functions. Overall, just evaluation that catch things that are more complex. Now we're making some progress towards that, but I think there's still room for improvements. And the last thing is that we need better, smaller, specialized models, because not everyone has enough resources to deploy 15 billion model or 7B model. So if we could generate smaller models that are better, that would be good too. So here I tried to show you a little bit how you go from just data on GitHub to actually products that you can use. For example, Hugging Chat and the VS Code, that extension that we have. And we saw that between the two, you kind of have to do a lot of things, not just train on a lot of GPUs, but you have to do a lot of data curation, data governance. You have to also work on inference to be able to serve a lot of users, and evaluation, and also fine-tuning. So thank you all for your attention. And if you have any questions, feel free to ask them, and you can also leave us some feedback.
Thank you, Loubna. Any questions? There's one here.
All right, thank you for your excellent talk. I've just got one question that has bothered me for a while. All the code that you suck in somehow from GitHub, you say you take care that the licenses are okay, so I guess there will be no GPL code in your or in all those large language models. But what about other licenses, and what is a permissive license? Because almost all the licenses I know say that you must leave intact the copyright header, that you must add the license file to the code that you're producing? Or is there any discussions in the community how to deal with that?
Yeah, that's a very good question. If you use MIT or Apache, that doesn't mean that you shouldn't attribute the author if the model generates exactly the same code. That's something we thought about, and we implemented code attribution tools. For example, if you use the VS Code extension with StarCoder, we have a membership test that when the model generates something, we go and check the dataset, and if we find that it is an exact copy of something that was in the dataset, you have like a red alert, and if you click on the link, you can find exactly which repository that was from, and then you can attribute the author. So that kind of tries to help a little bit with the code attribution side. So we try to develop some tools to help the users who are using the models to attribute the authors if the model ever generates exact copies of what was in the training data.
Any more questions?
So I have a question. So in training the model, do you care about the quality of the code? Say like if the code is neat enough and the algorithm's computational complexity?
Yeah, so for when we were training on the data set, I think you can implement a lot of filters to only keep the code files that you believe have a higher quality. And we did a lot of experiments and a lot of ablations to try to find the adequate filters. And we found that you can filter, but you shouldn't filter too aggressively. Otherwise, you will end up losing a lot of data, and you wouldn't have enough to train your model. For example, we have a paper called Santa Coder, Don't Reach for the Stars. And that's because we tried to use stars as a filtering approach. So for example, we kept only files that had more than 5 stars, but this significantly reduced the size of the data set, and we ended up with a model that was like the worst of all the models we trained. So some filters might seem like good to you, but maybe for the model training, it's not worth using them. So for example, filtering on stars is not a good idea, although we might be thinking that repositories with a lot of stars probably have a higher quality. But now we use some kind of basic filters to remove auto-generated files. For example, we count the average line length, and if we find that it's very long for some specific programming languages, maybe it is auto-generated. We also try to remove data, for example, CSV and JSON. We only keep a smaller subset because that is not code, just data. So we have other filters like that, but they are not too aggressive.
Thank you.
Sure.
Hello.
Yeah, there's someone.
Am I right to go here? My question is regarding, obviously, the legal and ethical considerations around scraping data from GitHub. For example, I know in the past there's been legal cases. One notable one would be the legal case between LinkedIn and HRQ, where HRQ were scraping data from LinkedIn using fake accounts, and I think LinkedIn took an injunction against them. I'm just wondering what considerations have been made in that sense. Is there some kind of agreement with between yourself and GitHub on the scraping of the data, or did you just go ahead and scrape the data?
Yeah. No, there's no agreement between us and GitHub because we only use the repositories that are public. And then once we scraped them, we filtered out, for example, licenses that don't allow commercial use or GPL code. And then we trained on a subset of the data that we scraped. And we have also these opt-out tools, so we can consider that, for example, giving users kind of a choice to decide whether they want their code to be included in the pre-trainings or not. So in this opt-out tool, users can fill a request, and if they see that some of their GitHub repositories are in the dataset and they want them removed, they can ask to remove that. And we also have the code attribution tools. So these are kind of the 3 things we try to consider, but we don't have an agreement with GitHub because the code was public. Does that answer your question? Okay.
We have one over here.
Hi, thank you for this great presentation. Do you have any mitigation against the risk of model collapse, where you put generated code back into the stack and where you train the new models on AI-generated code?
Yeah, I think there was a study about you're talking about using synthetic data, what the model generated to train again on it.
Yes, and then with a couple of cycles, the model collapses and then just spit out random things.
Yeah, I think maybe if we're talking about the same study, in that study they kind of used a very small model. I think it was OPT 125 million, and they found that it collapses. But now a lot of people are training on synthetic data, a little bit models that are larger, and we haven't seen that happens. The worst thing that happens is that the model's performance that just does not improve on the task you're training on. But maybe in the future when we have a lot of these cycles that will happen, but now that hasn't really happened.
Okay, thanks.
Yeah.
Another one.
Hi, thank you very much for the talk. The question is, if we come to a future where most of the code is AI generated and this is for sure being used to train more of these models, what do you think will happen?
That's a good question for which I'm not sure I have the answer. I think we're gonna have to wait and see what happens. But if we see the code that is being generated, a lot of it actually might be higher quality than if you take the average of what is on GitHub. So it's not just garbage code. But I think maybe something we can do is to kind of have things to detect and distinguish AI-generated code from code that was used by humans. For example, I saw a very recent paper that just a study where they tried to see which papers have been written by ChatGPT, and they used the word delve. And they found that after ChatGPT was released, the number of papers that use the word delve just increased, and ChatGPT has the tendency to generate that. So that's kind of a silly filter, but it still detects what was generated by a model. So maybe for code, if we can have some watermarking approach or something that will help us distinguish AI generated from non-AI generated, that would be very helpful. But I think that's still under exploration, and we haven't made much progress on that. But it's hard to predict what will happen when we will have more AI-generated code than human-generated code.
Thank you for your talk. My question is, looking forward to the future, can you sort of talk about how we might get to the point where you could generate multi-file or project size completions with one of these tools?
Yeah, I think that's something everyone's looking forward to. Because for example, when GitHub Copilot was introduced, I personally was using it just for documentation and tests. It was not very good at generating new code, coming up with new ideas. Now it has improved a lot, so you can use it for other tasks that are more complex. But I think we're still a little bit far from having something like an agent that can work on your whole code base, and just you give it a question. You don't need to say where exactly it has to change the code. So I think that is kind of the end goal, to have something that can take in multiple files and do the required changes. One step forward to that is training on repository context, for example, which we did for StarCoder 2 compared to StarCoder 1. But if we see things, for example, like Devin, if you saw it, it's this AI agent that can change anything. And I think that means that we're making progress towards that. You just need to find the right recipe for that. And I think that means that you need to have good instruction tuning data that not only asks the model an instruction about a specific code snippets, but something about a code base. And you also should start from a base model that is already very good, because that will significantly impact the performance of what you get. So I think that means having better base models and better data sets that you train on, and also better evaluations to be able to track if you're moving forward or not with regards to that aspect.
There's one over there, then here. Yeah, go on.
Training your LLM seems to be quite an involved process. Do you think there'll be a time where, when I'm in an enterprise and I've got a couple of Git repos, that I can just say, hey, model, please ingest these models, and then the model trains itself on my code without me going through this whole song and dance here?
Yeah, I think there are a lot of startups who are trying to do that, because that's kind of like a use case. I don't want to be involved in all of this training. Just give me a service that I can launch the training. So I think there's one probably called Poolside. And they're trying to have that, because basically now we have all the components. There's the model, there's the fine-tuning scripts, and there's your data, and we kind of know which filters will help. So we just need someone who will combine these components. So maybe, yeah, that's a product that someone can develop and you can use.
A bit of a follow-up on that, and I think you touched in your talk, but I didn't get the guidance. With respect to fine-tuning, you talked about your libraries, right? That you did fine-tuning for the libraries. So can you give some guidance of how many, I'm guessing, million lines of code would you need to fine-tune? Let's say I have, my own frameworks and libraries internally in my enterprise, and I want to fine-tune a model. Roughly, what are we talking about? We need 1 million, 5, 10, 50 million lines of code.
Yeah. I can give you a number, but like that number does not really apply. It depends on your use case, which model you started from, what you're trying to adapt it. But I think usually for like fine-tuning on new programming languages, not a new one that the model has already seen, but you want to improve the performance a little bit, maybe a few tens of gigabytes of data should do the trick. If you're not just do like instruction tuning or get the model to follow instructions, you need much less. I think people are just using tens of thousands of samples. But yeah, maybe a few gigabytes of data could work if it is just taking a model that has already seen that language and you just want to adapt it. That should work. For example, if you go to the blog post that I mentioned, I think they had even less because they just took the Hugging Face libraries. I don't know how many we have, but like they just compiled them into data sets and they found that it works to train on that. One other thing that's kind of made it that you need less data is these new fine-tuning techniques that don't take the whole model and change the whole weights during the fine-tuning. They only change specific weights and specific layers that they add. This means that you don't need a lot of data for the adaptation. So yeah, you will need to try and see at what threshold your model gets better.
Thank you.
Sure.
Hi, thanks for the talk. I have a quick question around if you've done any work on like deprecation of libraries or stuff like CVE. So I've got loads of examples, I guess, where ChatGPT will generate like a package JSON or dependency file, but then the library or API call that it's referenced in the next bit of code is deprecated or doesn't exist in like the V2 version. Have you done any work around how to sort of avoid that happening in code generation models?
Yeah, I haven't personally worked on that, but that is also like hallucination for LLMs when you would ask the model who's the president of the US and they would say Obama because like this is something that was deprecated, this is old. And one of the techniques to solve that is to use, for example, retrieval, RAG, to kind of retrieve information that is more recent and add it in the context. In your case, you could try to retrieve the documentation for the new version of the library and add it to the context to kind of tell the model, okay, these are the new changes that are changed, or you can also add the logs of the changes. But that is something that is worth exploring. Otherwise, you would need to fine-tune on like recent code. But these are two things, either retrieval or new fine-tuning.
Anybody else? Over there.
Hello, thank you for the talk. So we've had a truly explosive growth in AI over just the last few years. Do you think we're close to plateauing, or is this just a start?
Sorry, I haven't heard the last part.
Sorry, what?
I didn't hear the last part.
Are we close to plateauing on AI, or is this just a start?
I think we've made a lot of progress, but we still have a long way to go. First, by like matching the performance of the closed models, but then trying to address some issues that even these closed models still have, which are the hallucinations, the biases, and also all the data governance issues. So we think we're off to a good start, but we still have a lot of work. Like you asked, we want code models that can act as agents on programming code bases and not just complete a simple function. So we still have a long way to go, but I think we're off to a good path.
Thank you.
Sure.
We have time probably for just one more question, if somebody has one. No? Do you have an experience on using code generated to improve an existing code base, and how this is working well or not with code LLMs?
I think, yeah, this can happen implicitly when you have some engineers who are using the model and then they use the code that is generated for what they will push, for example, to production. So that's kind of an implicit improvement. Otherwise, you can maybe try to use the chat models and maybe integrate parts of your code base and try to get feedback on these different components. But yeah, it's still kind of, I think maybe early stage because we still don't have models that can act on the code base level, but they still all act on the file level. Yeah, but maybe it's a bit early stage to say.
Thanks a lot, Loubna.